5 to 10 minutes question answer discussion if you want, and I would invite you all to actually do that. Make use of it. For some it's the usual geospatial topics, of course, but others are new to it and might have other questions. It's 9 o'clock. The stage is yours.
Thanks. Thanks you came early in this morning, and the first presentation today is about how we can use deep learning to improve data quality from a data set, and here we took OpenStreetMap as an example. So the goal of this presentation is to show how we can detect inconsistency between two data sets. And between these two data sets, we can highlight where there is some issue that a human has to check to verify if everything is online, yes or no. How we do that with deep learning ecosystem, first is to bring imagery and related labels and to train neural networks with a loss function till we get a trained model able to use the very same kind of imagery to predict an answer. And as since we get a trained model and the ability to produce imagery, we are able then to compare between the prediction and the alternate data set. In our example, it will be here OpenStreetMap. So that's the main idea, to train a neural network to predict and to compare. That's the point. What we use to do so, we took roboset.ping with a semantic segmentation ecosystem able to deal especially with geospatial imagery and to perform some main feature as a dataset quality analysis, change detection, and feature extraction. So that will be the software, the tools able to help us to do that. What's the spirit about that is to bring the latest semantic segmentation state of art available in academic field, but to translate it in an industrial robust code and to allow by a modular design to extend and to write only the part you could want to make it your own. And the other point will be the ability to be well integrated in either OpenStreetMap or Mapbox ecosystem and to be geospatial compliant. How could it help us to make it work? First is to help the data preparation part. So as since we have several tools able to save us time on the data preparation, it will be really helpful. The first is the ability to use either raster or web services to create imagery. The other is the ability to use GeoJSON or OpenStreetMap files to create the labels. And as since we got both imagery and label, we are able to create our own training data set and so to play with. So the first interesting part is to help us to create easily a training data set. The other interesting part is the ability to reuse already trained model who came from ImageNet. And there is a lot of model already able to classify a feature from an image. So this is the internal representation of the model with the first part with the encoder who took an image, encoded it, and class every pixel among the output feature we want. And the other part is the decoder. And the point here is to reuse encoder pre-trained model to help us to be very accurate on the kind of classification we want. And in this really example, we reuse ResNet 50 as an encoder. The third part is the ability to perform accurate training from the couple. So here the image and the label are the input couple. And if we use a really classic loss function, we get this kind of output. It's a bit noisy. But if we use another kind of loss function, as these two ones, were far more designed to take in charge the semantic of the feature, we can, as a direct output, get something really more accurate and without all the noise that a classical loss function could bring us. And so the point here is to have something sharp enough to avoid the need of a post-process on the output. And as you can bet, what we use here in RobustSet Pink is a Lovatch semantic loss. The other point, I think we got the ecosystem able to deal with data and to train it in order to get a trained model, is what kind of data could we use to train the model. The fact is we don't have at this moment a really reliable open data set for geospatial data because all the labels we can grab are some part of creepy or not that accurate. And one point is to say, okay, how could we bootstrap a good open data set? The point here is to say, okay, we can reuse open data. To do that, as since we are able to filter them. So how could we do that? By reusing imagery from an open data. In this example, I took an example from a city in France who provide open data as a services. It's Lyon. And so I grab with WMS the imagery from an area, and here it's the coordinate from this area. So here, this is RobustSet Pink tools command. And with the only two commands, we can bring the imagery and add a tool to visualize it with Leaflet. We do the same with the labels. And so with the labels, we grab a GeoJSON with roof print from the very same area, and we rasterize them to convert from a vector to raster kind of data. And since we do that, we can split the data between a training and a validation. And here the few commands to help to split. And if we launch a first training, we get as an accuracy something after only 10 epochs, only on the building classification, with already like this kind of result. So it's already quite good, but we'll see how to improve it. And to improve it, the point is to remove all the labels who are not accurate enough to be used as a training in the training dataset. So if we look at the very first predict result, it's as simple as to launch on the train model with the image to create new mask in the output. How to detect if some prediction are not good enough is to launch a compare command between what we are supposed to get and what is created in the output. And we use three different kind of threshold The first one is related to the quality we want to get, and the other is related to how much feature are supposed to be in this tile. So I think there is enough feature considered in a tile, and if the quality is below a threshold, there is some pink area or spot on the map, and the point is to see that there is whole area where it could be either no feature to classify or good quality, and there is some other parts where obviously there is some issue. So it's the first way to focus on places who could imply that a human had to check. And if we zoom in a bit and more, indeed, in the places where some squares are spotted, it will mean that, for instance, labels are missed in the input data, and that there is something to do. Just to explain you, in pink, it's what is predicted by the model. So it's from the imagery what we predict. In green, it's what is supposed to be from the label. So it's from the GeoJSON file we grab. And in gray, it's when both are agreed. So it means that both the prediction and the label are agree on these very same pixels. So here we can spot at once that these buildings were supposed to be on the ground related to the imagery are not present in the label. So what we want here is to remove them because the core of this stuff is to say that if we've got garbage in, we will have a garbage out. So we want to remove all the labels who are not good enough to be used. And so there is another tool, still compare, but it's a side-by-side compare with the imagery and with the result. And here, in this example, there is some building stuff, and the label is not at this moment reliable on the imagery. So on this really one, because we selected with a lower quality of result, we can, by a human operation, remove it. And once we remove all those who are not good enough, we can remove them and launch again the training. And if we launch again with an accurate training data set, the quality of the results rise up. And obviously, if we train it longer, the quality will still rise and will be better. So it's the first way to save your time, either to grab data, to filter it, since you are able to get a good result for a trained model. And if we look at the output once we train it, we can compare side by side that, for instance, both are in line. So the imagery is in line with both the prediction and the labels, or that there is obviously some changes between the imagery and the labels. For instance, this part of the roof were not present on the initial label, so it's a change. Or it could be also a false prediction. In this case, it's a false negative because this one should be in a building. And the point there, once we are able to do that between the open data and the imagery, is to say, okay, what could we do now with the OpenStreetMap data? So we grab OpenStreetMap, we extract from the PDF to a JSON, we rasterize it on the really same way than before, and we can compare the result from the model we trained before between the OpenStreetMap data and get this kind of output with, for instance, here, buildings were not present on OpenStreetMap as buildings. So we'll see just after what it could mean. And once we do that, we have also the ability to vectorize it and to produce a new JSON and to do everything we want with that. So what could mean the different kind of color? If it's a green only, in this case, it could mean that it's present on OpenStreetMap, but there is nothing on the imagery related. So it could be either that the building was built since the imagery, or that the building was destroyed, but still present on OpenStreetMap, or it's an OpenStreetMap artifact. If it's only in pink, it could mean that it's predicted by imagery, but not in OpenStreetMap. So the first frequent use case is that the polygon is present in OpenStreetMap and not with the attribute as a building. So it's only an area. It's only a surface, so it's an attribute issue. But it could also mean that the building is really missing in OpenStreetMap, or that the building was destroyed since the imagery, or it could be also an artifact from the model prediction. Obviously not in this case. And the third kind of thing to take in consideration is also that it's not because you train it with some building label that the OpenStreetMap label buildings are always the same. For instance, here the parking are considered in OpenStreetMap as buildings. They are not considered in the open data from Ganlieu we took already as a building. So we have to be aware that we have to deal with closer attribute classification between the data we took as training and the one we want to compare with. If we look about the performances, for the whole data preparation, it's something, it's about 1 hour or two. If we look about the filtering part, it's a human part, so it depends on you, but it's something could be done in a small amount of time, something like 1 or 2 hours. The training part is the part of the process will consume the most of the time of the process. So with GPU, it's something like 20 minutes per epoch. So if we want to training till 100 epochs, it will be more than 1 day. And about the prediction, we are able only with a single GPU to perform up to 3 megapixels per second. So it's quite decent. And so the whole process will take something like 2 days between the download and all the prediction finished on the first time. Yes, one other point is if you have several GPU, it scales, so you could save time on this part. About the stack, so RobotSpink is on the reuse a lot of other existing software, obviously, and there are several stacks indeed involved. First one here is related to machine learning with PyTorch and DeepLearning. The other one here is related to imagery with Pillow and OpenCV. This one is related to the ability to deal with styles, and here it's the geospatial stacks. About the timeline, the initial project was provided by Daniel from initially from Mapbox, and the first release was RoboSap. there are several releases from RoboSat till the point that Daniel left Mapbox, and so RoboSat was no longer maintained, and so it began to be RoboSat Pink to took the next step and to reuse several features was initially bring to RoboSat, and to add and to focus in fact more with the quality of data rather than the extraction till now. What will be the next step? The next step will be the ability to deal also with lower imagery resolution. So now we use quite good imagery to perform this kind of prediction, but it will be more interesting to be able to do so with imagery as Sentinel-2 to keep improving the prediction performances. It's already good, but we bet we can do far more better. And next step will be also to provide a pre-trained model to allow you to directly predict and to not have to train again a model from ImageNet, but to do directly a pre-trained model, maybe to train it a bit with your really kind of imagery, but to save time on the training part. As a takeaway, right now you can have state-of-art semantic segmentation ecosystem available and playful. It's on these few command lines. You can use plain open data to train a model, and the next step will be to improve the predict speed performances to be able to scale at large. Because here we are talking about a big city. We are not talking about a country or a continent or the world. So if we want to scale at large, we bet that this part will mean. And that's it. Thanks.
Questions from the audience? I see one there.
Regarding the performance.
Could you sort of speak up a little for the microphone? Sorry about that.
Yeah. Regarding the performance figures, the 2 hours for manual filtering and the 20 minutes break.
Yeah.
For what number of tiles are they?
On the manual filtering, we so on the training, it's something like 2,000 tiles, each of 512 pixels square. And about the manual filtering, I grow something like 100. It's 1,000 tiles, and I remove something half about them. Yeah.
Okay.
Yeah.
Anybody else? Please.
How specific is the model it builds to a particular region of the world?
The model train is first specific to the kind of imagery we grab. So if you grab a different kind of imagery with a different radiometric calibration, your model will not be that good first. And if you change your landscape, indeed, it will not be accurate either. So if you want a model able to scale, you have to cherry pick a lot of different kind of landscape to have something able to be representative to what you are supposed to classify. And it's a part of the process to be sure that you get enough of each different kind of landscape to train your model. Yeah.
There was one question.
Same question as
Oh, okay.
Question about, have you thought about or tried to use the system for other features other than buildings?
Yeah. Right now, on RoboSat Pink, there is already the ability to extract roads from the PDF, so that's the first part. And as soon as you get the labels here, you can classify what you want. So even if right now you can already grab easily buildings and roads, if you have already other kind of feature you want to classify, it's up to you. The only point is that what you want to classify should not be too sparse on the landscape. So for building and roads, it's not an issue. But if you want to classify something really specific, it could be a bit tricky. If your model is trained to say always no, it will be difficult for him to say yes when you have to. So I think it's not too sparse, it will be fine.
Anybody else? Question? We are really good in time, so please take advantage.
You know maybe about what will be ready for Sentinel-2 imagery? You were saying what's the next steps?
Yeah, the point on the point here to be able to use it with lower resolution will be on two parts. First one is with Sentinel-2, we have a multi-band data, and so right now RoboSat Pink is able to deal with multi-band imagery for training, but not yet for prediction. So it's something must be improved. And the other part is the resolution. So here we play with alpha meter resolution per pixel, and here we are talking about 10 meter per pixel. So obviously we perfectly know we can't perform feature extraction from a low resolution, but we want to be able to perform quality of data, and so to spot if in a place, for instance, buildings are missing or roads are missing. So not to perform a feature extraction level, but to be able to say that here something is missing or something is not accurate enough, and so a human have to check it again. One key will be the ability to use a superpixel solution, who can help to increase the quality of an imagery when you zoom in. It's a kind of interpolation, but with a better output resolution.
I would like to know how difficult is it to get their imagery to use for your algorithm, because I think having that at a high frequency to see changes would be important.
The point is, since we are using neural networks, they are able to learn patterns from the imagery, since you provide enough information. So, for instance, one thing a bit tricky with a classical classification system is to handle shadows. And here, we don't have to bother with that, because we provide enough information and labels, and so the neural network is able to deal with. Is it your question?
No, I didn't catch it exactly.
Okay.
I was rather asking about the image data sources.
Yeah.
How to deal with that, because I think that can be difficult, from which satellites to get your images from. To get it often, once a week, once a year.
In this example, I use open data because it's available, and because on this use case they are quite recent. If we are talking about Sentinel-2, it's a week update. So as since there is no cloud, you can pick your time frame as you want,
Okay.
or as you need.
Okay, thank you.
Anybody else? Perhaps you have a question to the audience?
Do you see, does it change something to you? Is it something who could open some new usage from or not yet?
Well, my case, like if we are using training data for classification, and when
Yep.
we want to retrieve training data of known forests, for
Uh-huh.
instance, it's really a pain in the ass to clean the
Yeah.
training data
Yeah.
for roads, buildings.
Yeah,
So this could be quite
Yeah.
interesting.
yeah. Mm-mm.
Do you think it's got potential to be better at humans than spotting things in low quality imagery?
It's designed for. Yeah, it's the first design is that, and as since we got a good quality on the prediction, we can perform a feature extraction. But the first point, as you said both, is to help to save time on the training data set qualification, and then to qualify the data set to something else. So yes, the point is to spot where a human has to give a look, and so to save his time.
Regarding your question,
Yeah.
see it from the standpoint of the user.
Yeah,
OSM data is, well, depends on the walk or the visit density,
Uh-huh.
how frequently a place has been visited,
Mhm.
and if it's how could you call it, an outbound area or somewhere where
Mhm.
some dead end street or so, then there are many cases when you find ways or buildings or whatever
Uh-huh.
features which you haven't found on the website,
Mhm.
and it might be a possibility, for instance, before the next vacation, to simply run over this area, to run over satellite images of this area, and then you get better maps for this area. This would be an option, but to shrink the hope is the last recent time this happened to me was
Mhm.
2 weeks ago or so, and it was in the wood,
Mhm.
so no possibility to find them with satellite images.
Mhm.
But anyway, in other cases, yes,
Mhm.
I made this experience in the past, and
Mm.
as I said, and it would be helpful.
Mhm. Okay.
I have a question on that side.
Yes, I have a use case, but I haven't yet looked at the
Mhm.
data available in OSM
Mhm.
to identify graves in a cemetery.
Mhm.
Do you think it would be possible to use your?
The point is really to first to think about sparsity, and second is do you have labels accurate enough? Yes or no? Since you these 2 points are okay, it leads to play more. On your use case, the first point, is it too sparse? It really depends on which area you take in charge. If you took only specific area related to graves, or to cemetery, it could be not that sparse, but you will need an high resolution and imagery, and you will need labels accurate enough to train a model. So, as since you get that, you can play with. But if you only have plain imagery and took the whole city area and want to spot graves, it will be difficult.
Could one also use it? For me, we work at Navid more with GPS navigation. Would be also possible to detect, for example, road construction, to then add that
Yeah, because it will be a chain detection. It will be something like that. So yes, you can spot it. Yeah.
That's more use case from our side maybe.
Mhm. Yes.
Okay.
Okay. So
That's it?
okay. So thanks.
Thank you very much.
Thanks.
I'd like to invite the next speaker to plug his in or perhaps use one that is available.
No, thanks. Thanks for the talk. Yes.
Take care of it. That doesn't
How's it going?
Hi, I'm Mark.
Hello.
Nice to meet you too. It's we are really good for time, but I'm going to have to be strict with the scheduling of the AV podcast. So my question is, we are scheduling from 9:45 to 10:15, and maybe you want to leave some 5 to 10 minutes, possibly a question and answer session. Yeah?
No problem.
Okay. I'll,
Let's see if we can figure this out.
Time I'm going to give you some advanced warnings.
Alright, that's gonna be helpful. Well, I can keep my phone here so I can.
The AV sound system doesn't seem to work properly, so if you could talk a little bit louder,
Oh,
that's hopefully no problem.
no problem. Is this something I have to wear?
Yeah, that's what was the audio, is the
Oh.
microphone that is a little bit iffy.
You want to say something like that or not?
Let me see if this works first. Oh, there you go. I think it's my nail over there. Okay. But for some reason, no, it's online. Like I just need internet access. So basically, I just need to go to FOSDEM.
You know to play with?
Oh, this.
It's next.
Previous
Previous
next.
next. Okay. This one or in this example, it's quite high resolution, but not on a specific area, not a worldwide level. There is a project to together all the imagery that people want to define, obviously it's only on specific places, but there is more imagery available. So it's also